video, we already know how to build up this process model, CTOV, constant velocity magnitude, and constant turning rate. And we also know why we need to build up this model. It's hard to estimate the state of the object correctly when the object goes into turn. And we also know how to create a state variable for this model and how to build up the process noise, how the influence the process noise into the state variable vector, right? And let's talk a little bit about the Unscented transformation. Okay, and today we learn how to apply Unscented transformation to solve this problem. In the UKF, we also have the two important steps: prediction step and measurement of the step. In the prediction step, right now we go detail step by step right here. Generate sigma point. How to generate sigma point? Okay. For example, in this our problem, we have the state vector. What the dimension right here? 5, right? We have the PSBY velocity, yaw angle and yaw angle rate, right? And state dimension right here 5. And we have the formula to generate sigma point. How many is the sigma points we need? We use this formula, right? We plug it 5 right here. We have the 11 sigma point. Each sigma point they include up PSBY, B, yaw and yaw rate. So in this case, you will have the and you will have the one matrix sigma point 5 row and 11 column, right? Another example, quite more simple right here. For example, we state vector 2 PSPY, and state dimension we easily know is 2, right? And plug into the sigma point right here. You know the number of sigma point is 5, right? And what the matrix the sigma point we create? It means 2 by 5 times 5, right? So all the sigma points we create put into the matrix, we call the matrix sigma points right here. Remember that. And for example, right here we have the example right here, state vector is 2, and we have the means and covariant matrix right here. And how we know for each sigma point right here, how we know how much for this one, for this one, for this one. Okay, we have the rule of the sigma points, generate sigma point right here. Look at the formula, is all from so, but the way we find sigma points quite easy right here. Look at in the matrix sigma point right here, we have the mean state, the first sigma point, right? And another 2 sigma point right here, mean state plus square root of lambda plus same dimension times square root of the covariant matrix. And another 2 sigma points right here is opposite side minus right here, right? And what the lambda? Lambda is a design parameter. They show us how far spreading of the sigma point. Okay. And one more thing we had to know is the we will call A equals square root pk, right? Square root pk. In the C++ code, you will have the library. It means the Egan library help you to get square root the covariant matrix right here. So we go to find the sigma point for this example. The first one, we use the mean state right here. How about another 2 sigma point? For example, right here you have square root pk. There are 2 vectors right here. When you plus with the mean state and you times square root of lambda plus ns right here, you have another 2 sigma points generated, right? And we apply the same way for the opposite side. Means that minus, not plus, minus square root of lambda plus dimension times a. They generate 2 vectors for you. Okay. Right here, you see we have the A equals square root covariant matrix right here, 2 vectors right here. What we put into the formula right here, they create 2. They create the 2 vectors for you. Okay. One right here and one right here. Okay. And how to find another last two symbol point? You use the same way, and they will generate for you two symbol point right here. Okay, let's plug into the formula. You see, I know you how to do that. It's square root this one, okay, and time right here. For example, we have the state dimension right here is the PSPY. It means 2, 3 plus 2, 1. 1 plus here right here, 1 plus lambda 1 plus the ns of 2 is 3. 3 times square root of pk right here, and you minus this one, you get another 2 vector. Okay, right here. So total, you already had a 5, right? That's the way we generate the sigma point. Okay, and remember the matrix of sigma point right here. You know the dimensions. How you have to know the matrix of the sigma point, the dimension. Because when into C++, you have to declare the matrix, and you have to know the matrix right here, how many row and how many column. I think you already get it, right? For each right here, each column right here is state vector. Okay, sigma point, they include all the state vector, 1 column, 2, 3, 4, 5 sigma point right here. It means we have a 5 column right here and 2 row. For example, we have the 2 row and 5 column. For example, we have the 5 variable. We will have to the how much? If we have the 5 variable, we plug into formula, we have the 11 sigma point. It means 11 column right here. Each column, they include all the state variable vector. It means 5 times 11. Okay. Okay, go to the small example how to do the generate symbol point in C++ code. Okay, right here we create a class UKF. In class UKF, they will help you generate the sigma point. Alright, okay. This is a symbol class right here, right? You declare constructor and the constructor, and right here there's a function of symbol point. Okay, there are argument is now right here. There's a pointer, right? And we have the state dimension right here. You remember that we have state dimension is 5. PS, PY, V, your array. So total is 5, and it's a 5. Okay, and lambda, you use formula lambda equal 3 minus ns, right? And we have the means right here, mean state and the covariance state. Okay, at the time t equal k, you remember that. Okay, and we have the, for the first time we have the PS, PY, V, your, and PS, PY, V, your angle rate, right? And we got a covariance matrix. Okay, 5 times 5 right here. Okay, and we create the matrix of the sigma point matrix right here. I told you you have to know the row, how many row, how many column. Okay, and after that you get square matrix of the covariance matrix. In the Egan library, they have the function help you to get the square root matrix, covariance matrix. Okay, and you remember into the matrix, the first column is equals mean state, right? Okay, I will go back and show you. Right, the first right here column is the mean state. Okay, right here the first column is, you get the value of the mean state put into the first column. It means the first sigma point. Okay, and what about another column, another sigma point? We run the for loop right here with +1 for another column 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10, 11. So we have total 11 column, right? Each column they have a value. you know this, you use the matrix mean state plus square root lambda plus dash time a column right here. This formula, right? And another formula we put here. Okay, and the will generate for us the simple point matrix right here. The expected result right here. You see, the first column is the mean state, and another column you get another simple point right here. Let's generate total 11 column, 5 rows. Okay, and in the mains, that's called the UKF class and generates the simple point for us. Okay, we create the matrix 5 times. Okay, 5 times 11, 5 row and 11 column right here. Okay, let's run it and see how we generate the simple points. Okay, you can see that we create the simple point. The first mean, okay, mean state, another simple point right here, total 11 column, 5 row. Each column, you see they have included state vector variable, PS, By, V, velocity, your angle ray, okay. That's a basic way to generate simple point. Okay, we continue the so we already know the simple point, okay, and right now we pass through process model. But into the process model, we not only the simple point, we include up the process node right here. Process node right here, right? That's the nonlinear function, right? Nonlinear function process node. Yeah. So right here, you have to now look at the process model. This process model right here, right? That's the two. Sometimes people write detail how the impact of the process node to state variable at time between time t equal k 2 time t equal k plus 1. We can see, look at the formula right here. You can see easily the process node mu k right here. How the delta t and the impact of delta t and your longitude acceleration, and so the your angle acceleration impact to this state variable. But sometimes you see people write the process node this right here. That's the mu a and mu your acceleration. Why? When we write something like this, mean we say independent noise process. That doesn't express any effect on the state vector independent of the delta t, right? So every time we talk about UKF, Unscented Kalman filter, and with process noise, we talk about the process noise. We say this matrix, right? And this, this matrix is the distribution with the mean and that's the mean 0 and the covariance sigma a square and sigma your acceleration square. Okay, and we have the process node covariance matrix right here. You see, we have right here sigma a square and sigma acceleration your angle square, and to this value is equal to 0 because longitude acceleration and your acceleration is independent. Okay, independent vector, they not relate together. Okay, so and right now we already know the covariance matrix. Okay, how we put and how we pass the simple point with including the process node into the matrix. We have right now we have the state vector. Remember, we have state vector. We have the phi, right? PSPYV, y-angle ray, and state dimension right here. We have the number of sigma point right here, the 11 sigma point, meaning the equivalent column into the sigma point matrix, right? And we calculate the sigma point with the formula and lambda right here. Remember that, okay? And right here we want to add the processional into the sigma point matrix. So we call the augmented sigma point matrix. So our augmented state means we include the state vector variable right here, and we add two more variable right here, so mu a and mu accelerate your angle right here. So right here we have augmented state dimension is equal 7 right now, okay? And you know the number of sigma point right here is the 11. Right now we have the 7, so 7 right here we plug into the formula. We have a 15 column, okay? So we have 15 sigma points and 7 row. And when so use the same thing to generate sigma point, the formula generates sigma point right here. And we have we also have the covariant matrix. Augmented covariant matrix is the combines the, you see the we combine the covariant matrix right here, and we add the two we add the processional matrix right here, and they create a 7 times 7 row and 7 column for the augmented covariant matrix. It means you already have the matrix sigma point matrix, augmented sigma point matrix. You also have the augmented covariant matrix. Okay. Okay, we do the next step to create augmented sigma point matrix. Okay, how to do that? Look at the Okay, we also have the class UKF right here. Last time we learned how to generate the sigma point. Right now we start with the generate sigma point, include of the processional inside, right? Right here we create the augmented sigma point right here. The same thing, but the name is quite a little bit different right here. Augmented sigma point, they have to include in this processional inside. Right now we have the state dimension, so have 5 VPS, PY, V, and your array, right? And right now we have set augmented right here, state dimension is 7, right? Not 5. Last time we learned how to do that, right? But this one we start jump to the first step, generate sigma point, okay, for the model. And we assume the noise right here, mu a for acceleration is 0.2, and for the your angle as your acceleration right here is 0.2, okay? And we apply the lambda right here, okay, with the same way right here. And we also have the mean state. You look, I think you understand right here, quite similar example. And we have the covariant matrix right here, right? But remember, when we told you we create augmented covariant matrix. Covariant matrix is the combine two last column, okay? Two last column in this matrix, and we keep the same BK right here, but we only add the Q matrix right here, okay? So how to do that? Okay, we create a 7 by 7, the 7 by 7 augmented covariant matrix right here, okay? And use it, and we also the augmented the sigma point matrix right now. You see, equals 7. Augmented right now is 7 times 7 times 2 plus 1, 7 row and 15 column, right? You remember how we create the augmented covariant matrix? You see, we say we fill up the covariant, we create a P augmented right here, 0, 0, all 0, and we got the top left corner 5 times 5 equal B, right? Where 5 row and 5 column of the top left equal B, okay? It means it's the same covariant matrix, and another position in the 7 by 7 matrix is your angle A, and your acceleration and your longitude acceleration. It's hard to see, hard for you to see right here, but I'll show you later. And we also have the square root matrix right here. And we created the input S right here. We have the 5 vector right here. And it means right here we create augmented mean state. And continue, we go to the another column. You see, first we create the first column of this matrix is mean equal the S augmented right here. Is the first column equals they mean, right? And next second to 15 you apply the formula S plus square root right here, right? And you plug into the matrix right here. That's it. I hope you understand. And the result is best something like this, okay? We have the first column right here, the mean state, right? The mean state, but you have to add 0, 0 right here. And you remember how we add the noise right here, the process noise right here. Okay, two last column, right? Last time, two last column, sigma h square and sigma acceleration square right here. Okay. See the create augmented mean state right here. I think you understand how to do that. Okay, they create our augmented sigma point right here. They got the 7 row and 15 column. This sigma point, okay, each column is sigma point first, but right now we have to add the noise, okay, represent noise into the sigma point, augmented the sigma matrix, okay. Okay, so you can see here is the description of how we use the Eigen library inside. The code C++ code, I think you understand that. Okay, we already generate sigma point. So what the next step in prediction? We have to predict the sigma point, right? After generate sigma point, we predict the sigma point. Look like the picture right here. We predict we know to generate the sigma point right here. So right now we have to predict the sigma point right here. We pass through we have to pass through the process model right here to know predict the sigma point right here. Okay. After we know this step, we have to predict the covariant and mean state. Okay. What the next step? Okay. How about after generate sigma point, augmented sigma point, you continue with the next step, predict the sigma points. Okay. we already have the matrix augmented sigma point right here. You pass through the model, you get the prediction, the sigma point, okay, times k plus 1, right? And we already know in augmented state we have the 7 by 7 state vector variable. You have the 7 variable right here, PS, PY, V, your rates, and we add to more right here the processional acceleration and your angular acceleration right here. But in the predict state, we only need the phi, okay? We only PS, PY, V, your rate. So right here we have the matrix right here. You remember that we create a matrix 7 times 11 for the augmented state. Remember that right here. You already print this result. You have the 15 and 7 times 15. This column right here you have the sigma point right here, and in sigma point you have the state variable vector right here, right? But right here we only need to a 5 state variable vector right here. We don't need all of them. Okay, so when you pass through the process model, you only 5 state variable right here. You print the sigma point for the state. Okay, and how to do that? You remember the process model, our process model right here. Right now you have to get 5 vector right here, 5 state variable right here. That's only 5. We don't need that one. And pass through this model, process model, you get the predicted state. Okay, at time k plus 1, right? So how to do that? Okay, there's a formula for the process noise. Okay, you remember when the yield rate last video where I told you it's when the yield rate is not 0, it's different. When the yield rate is 0, it's go to straight, right? The objects go to straight, okay? And the formula right here, but it's not straight. We have the process model right here, right? Okay, how to do in the C++ code? Okay, we also have the UKFD. Okay, we have the UKF right here. Glass right here. We also have the sigma point. We also have a sigma point prediction. Okay, after we already have the augmented sigma point, we continue with another step is sigma point prediction at time k plus 1. We pass through all the value. Remember this one. That's the matrix we already create from the first step. That's the augmented matrix, right? Right here, the 7 times 15. But when we pass through the model, that's only 5 state variable vector for each column right here, right? So we have to extract the value from this matrix. Okay, that's the reason we have to extract the value right here. PS, PY, we got the each value from this matrix, right? We run the follow from 0 to the 15, right? And we got the each value, PS, PY, your V, your dot, mu, A, and mu, your dot right here. You see, we got each value from here. Okay, actually we only yield 1, 2, 3, the first 2 value right here. Okay, for calculation prediction, sigma point. And after we extract the value from this augmented sigma point, we pass through the model right here. You see, we have 2 cases right here. If the case goes 0, we have PS, PY. Okay, right here. If your rate is different 0, we have the formula right here, and it's 0, we apply this formula to calculate the PS, PY. And so we also have the V, and similar we have the V and your and your dot. Okay, we have the formula to figure out how to do that. After that, you remember what the formula right here, right? When your rate equals 0, we have a formula right here. Right here, after we add noise, the formula noise right here. And we push all the value, a new value calculation after push through process model. You got the predict sigma point, right? You put all into the matrix sigma point predict, and you just print it out. Okay. So let's see how they print out first. In the main, we just call the function sigma point right here. So right now, after we pass through process model, we have the sigma point prediction, right? Right now we have the 15 column, but we only the five state variable for each column, right? So it's good, right? I hope you understand that. Okay. Continue, we already predict the sigma point. So the last step in prediction step, it means predict the mean and covariance matrix. Okay. After we already have this predict the sigma point. So what the prediction mean and covariance matrix? Right here, you can see from the sigma point we generate right here, we pass from augmented sigma point from right here, you generate and you pass through process model, you create the prediction sigma point right here. So when we already have sigma point right here, how we predict the state, and mean state and covariance matrix right here, time k plus 1, how we do that. So we have a formula to predict the mean and predict the covariance. The formula right here, you see. But right here is a little bit different. We add the weight E, Vi right here for each column. Okay, each sigma point. So how we calculate the weight right here? The other formula weight right here is related to the lambda we talked before. Why? Let's think it like this. We already have in the first time you already have the covariance matrix and mean state. You want to generate the sigma point, you need the lambda, right, to see how far the is sigma point. Right now we do the inverse step. We already have a sigma point, so now we want to predict the state, mean state, and covariance matrix. We need the lambda right here. It's inverse step, okay? So, and we have to, we have to the sigma points generate here. We have the predicted covariance formula right here and weight right here. So let's jump to the code. How to get that value for the mean state, and covariance. Okay, it's the same last time. The structure of the code require the same last time. We create the class UKF and we create the function print the mean and covariance matrix. Right here, the two variable we need is mean state S and P covariance matrix right here. From last step, we already create the simple point prediction right here. Simple point prediction matrix. 5 times 11, right? 5 times 15, right? 5 state variable vector, and for each column, we have the 15 columns right here, right? And we know how to figure out how to find the S and P for prediction state and predict the covariance matrix. We know the formula we create the lambda, okay? Right here. We had to do everything the formula we create a lambda, right? And we apply the formula predict mean and predict covariance right here to get the value. Okay, predict the mean state. After we create a lambda for each simple point. Okay. Right here we predict the mean state. We use the formula, you see. And we also predict the covariance matrix. Let's look at the formula a little bit. They calculate right here predict covariance sum of the difference between the mean state from prediction to mean state right here. Okay. You apply the formula right here. You see. Transpose. Okay. This formula, you put everything right here. And this formula, S right here, wait time to right here. Okay. And let's run to see how they create. Okay, we see that in the predict state, they predict state and predict the covariance matrix for us. State we have the 5 state variable vector and we have covariance matrix 5 times 5 right here. Okay, so that's the 3 example in the predict state. Okay, I hope you understand. And next video I go detail for next state. It means the update state. I don't want to talk too much in the one video because you feel really confused. So let's go over the 3 steps. Okay, right here in the prediction step. The first time you have to create the augmented simple point matrix, right? It's a 7 times 15. Okay, After that, you already generate the sigma point. After that, you go to the predicted sigma points. You already 7 times 15 column right here. You pass through the model. You predict the state. Okay, predict sigma point. Okay, time k plus 1. Right now, you only need the 5-state variable vector. So you extract this matrix, okay, and you pass through the formula we through a set model. You got the predicted predicting the sigma point, okay, at time tk plus 1, okay. You see right here 7 times 15, you need only 5 times 15 matrix. Okay, this is the formula we pass through the value through the state variable vector into the state model right here. You got a new one, and the last step, after we already get sigma point, you predict the how the covariant and state vector in this one. Okay, you also use the formula right here. And you add the weights right here, and you apply the formula right here. Use the formula calculate the predict covariance right here, predict covariance and the covariance. Okay, you got the formula right here. You got the mean state and covariance, predict covariance. Everything we predict means and predict the covariance this matrix. Okay, right now a little bit different. You create a waste right here. That's this written step. If you don't understand, try to read again. Okay.